To run artificial intelligence locally, the standard approach is to open the Hugging Face leaderboard and look for the absolute largest models available, like DeepSeek R1 671B or Llama 3.3 70B. But when you try to force a 70 billion parameter model into a standard consumer machine, the system will likely crash or generate text at a painfully slow rate of less than 1 token per second. The alternative is to use small language models, or SLMs, that operate under 15 billion parameters. SLMs are compact AI networks designed specifically to run efficiently in resource-constrained hardware environments. The old trade-off was simply choosing between capability and size, but the new reality requires matching strict hardware constraints with highly specialized tasks. You can run fully private, offline, fast AI on your own hardware right now, but you have to abandon the desire for a single, massive model that does everything perfectly. The absolute dictator of what your machine can physically run is its VRAM. Video RAM is the dedicated memory on your graphics card that dictates exactly how much AI data your system can hold at one time. Parameter sizes required for GPT-4 level performance plummeted between 2024 and 2026, while average consumer VRAM flatlined. The breakthrough bridging this gap is distillation, a process where small models learn to mimic the complex reasoning of massive frontier-grade networks. Success in local AI is no longer about finding the smartest model in the world. It's about meticulously matching the right specialized model to the strict physical limits of your hardware. This flowchart maps out the hardware spectrum, showing that deploying local AI must begin with one fundamental calculation: identifying your total system VRAM. We start at the lowest branch, the edge and mobile tier, for systems with 4 to 8 gigabytes of VRAM. The primary advantage of deploying models here, like 5.4 Mini Instruct or Small LM33B, is achieving real-time, localized inference on standard laptops and edge devices without needing a dedicated server. The functional trade-offs are severe. These models suffer from weak multi-step reasoning and limited context windows. A context window is strictly the maximum amount of text the model can process and remember in a single interaction. Because of strict memory limitations, sub-8 gigabyte models will reliably fail at complex agentic coding workflows. Agentic coding involves an AI system autonomously writing, testing, and debugging software across multiple independent steps. However, you can still use specialized tools like Qwen 3.5 0.8b to handle extremely fast vision-to-text generation tasks within this memory footprint. You must also avoid triggering thinking mode at the sub-1 billion parameter scale, as the limited architecture frequently results in infinite, unstable generation loops. The 4 to 8 gigabyte tier delivers zero latency privacy for basic conversational tasks, but it demands strict system guardrails to prevent total logic breakdowns. Moving up the hardware spectrum brings us to the middle and most heavily populated branch, the 8 to 16 gigabyte consumer sweet spot. The heavy hitters in this category are models like DeepSeek R1 Distill Llama 8B and Microsoft's 5.4 14B. These models inject GPT-4 level math and logic directly into a standard RTX 4070 or Mac by utilizing distilled chain-of-thought reasoning. Chain-of-thought is a generation technique where the AI explicitly writes out its step-by-step intermediate logic before arriving at a final answer. This diagram illustrates the mandatory mathematical compromise, 4-bit quantization. This compression technique reduces a model's memory footprint by rounding its numerical weights into lower precision formats. In practice, Q4 quantization violently squeezes a 14 billion parameter model into just 8.4 gigabytes of VRAM.
Academic testing proves this Q4 compression causes virtually zero impact on actual model calibration or the number of dead neurons. Dead neurons are components within a neural network that stop responding to inputs and contribute nothing to the final output. There is, however, a secondary hidden cost to running distilled reasoning models at this tier, and it lies entirely in the generation process. The internal reasoning tokens generated during chain of thought eat aggressively into your usable context window, which strictly limits the amount of external document data you can ingest in a single prompt. The 8 to 16 gigabyte tier represents the ultimate value play in 2026, forcing you to trade a slice of context length in exchange for world-class quantized logic. The final hardware branch is the prosumer category, covering systems with 16 to 24 gigabytes of VRAM. Deploying massive SLMs like Qwen332B requires high-end hardware like an RTX 5090 or a Mac Studio. Operating here gives you flawless, desktop-level access to frontier-grade coding performance and massive 128K context windows that allow for full, unedited document ingestion. The trade-offs are a heavy upfront capital investment of thousands of dollars in GPUs and the complex challenge of managing the KV cache. The KV cache is a memory mechanism that stores previously computed tokens to speed up generation, but it grows continuously as a conversation lengthens. Operating strictly at the 24 gigabyte tier transcends running a simple desktop chatbot. You are hosting a private, enterprise-grade reasoning engine. This comparison matrix transitions hardware theory into specific, practical application scenarios. Our first profile is an indie coder utilizing a MacBook Pro with 16 gigabytes of unified memory. This specific configuration delivers world-class offline logic, but it dictates that the coder must limit the size of the codebase they analyze in any single prompt. The second profile is a private enterprise building an offline RAG system to analyze sensitive legal and financial PDFs on low-end legacy CPUs. RAG, or Retrieval Augmented Generation, is a framework that fetches relevant information from a private database and feeds it to the AI to answer specific queries. Utilizing the BGE-M3 embedding tool allows for an entirely air-gapped CPU deployment, bypassing the need for expensive enterprise GPUs. An embedding tool is a model that converts text documents into numerical vectors so the AI can quickly search and retrieve relevant concepts. The architectural bottleneck of this setup is 5.4's strict 16K context limit, which requires the enterprise to aggressively chunk their retrieved PDFs into smaller fragments before the AI reads them. Successful real-world AI deployment is never about raw compute power. It is about perfectly aligning the model architecture, the embedding tool, and the physical hardware constraints. The final operational hurdle is the software execution layer required to load these models into memory. You have to weigh the instant command line simplicity of an ecosystem like Ollama against the polished, granular interface of LM Studio. The specific trade-off of using these easy one-click tools is sacrificing the extreme throughput optimizations and granular performance tuning available in enterprise-grade engines like VLLM. VLLM is a high-throughput memory management engine built specifically for serving AI models at a massive scale. Zooming out to evaluate the macro perspective of the 2026 AI landscape reveals a clear picture. The absolute frontier of artificial intelligence is no longer restricted behind the paywalls of billion-dollar server farms. By mastering VRAM limits and deploying highly specialized, distilled SLMs, the bleeding edge of global intelligence now runs cleanly, quietly, and entirely privately directly on the desk in front of you.